Hello. Suppose you have an equipment with 12 volts DC power supply, and in that equipment you have a component which requires 25 volts. You would like to step up that 12 volts so that you can get 25 volts and use it for that component. Such a circuit exists, and it is of course called a boost DC-DC converter or a step-up DC-DC converter. The boost DC-DC converter has two modes of operation, one continuous conduction mode and another discontinuous conduction mode. In this video, we will see the operation under continuous conduction mode. With that as our aim, let's get started. There are four converters which may be considered basic converters in power electronics. One, buck converter or step-down DC-DC converter. The second is the boost DC-DC converter, which we are going to go through in this video and a few of the subsequent videos. Then a third converter which combines the buck function and the boost function, that is the step-down function and the step-up function. Obviously, it is called as the buck-boost converter. And a fourth converter called the Chook converter, named after the inventor, which is a boost buck converter. Basically, the order of the functions within the converter are reversed. In this video, we will be looking at the boost converter. Boost converter is a very popular converter. It has several applications. One of the applications we have already seen, that is the onboard power supply to boost that 12 volts into 25 volts so that some specific component can be powered. Another popular application of a boost converter is in phone, laptop and other chargers, other power supplies. These are called universal input DC power supplies. So whether the AC power is 230 volts 50 Hz or 110 volts 60 Hz, you don't have to change the charger these days thanks to the boost converter. Boost converter makes it possible to achieve this functionality. Another application we can think of is in solar PV systems. The solar panel are connected in series to form a string, and a few strings are paralleled. This whole setup feeds a solar inverter. The string voltages may not be the same, so the paralleling becomes problematic. So one solution is to use a boost converter in each string to boost up the voltage to a common level, and then you parallel the outputs of these strings and then feed the inverter. Such an application is possible for a boost converter. Boost converter, as we mentioned earlier, has two modes of operation. One continuous conduction mode of operation, CCM in short. Here, during one switching period, the converter undergoes two intervals of operation. The second mode or region of operation of a boost converter is discontinuous conduction mode or DCM. Here, the converter undergoes three intervals of operation in a switching cycle. The performance of the converter, as we would expect, is quite different in these two modes of operation, and a designer should understand both these regions of operation. This is a boost converter. It uses a power MOSFET as the switch. In analyzing this converter, we will make the usual three assumptions. One is that the components are ideal, the switch is ideal, the diode is ideal, and so on. There is no power loss anywhere in the circuit. Second is that the circuit has already gone through a transient and has reached a steady state. We will be directly jumping into the steady state and analyzing the steady state. We will not be focusing on how it reaches the steady state. The third assumption we make is the output voltage is nearly constant. That means the capacitor C is quite large. The output voltage is practically a DC. Whatever ripple voltage, AC voltage that rides on the capacitor is pretty small relative to the DC voltage magnitude. We are assuming that the components are ideal and lossless. That means we are not really going to be focusing on the characteristics of the power MOSFET so that we can replace the switch by an ideal switch. We'll be considering an ideal switch, an ideal diode, and an ideal inductor and capacitor in analyzing this boost converter and understanding its operation. There is a video on why in power electronics we tend to understand the converters in terms of ideal switches. That is PE18 video. You may wish to go through it. Next, we will see the basic operation of the boost converter under continuous conduction mode. This is the boost converter. Now, consider a situation where the boost converter is connected and the switch is not switched on at all. Even then, notice that there is a path for current flow. The source, the inductor, the diode, the capacitor, and the load are all connected together. So a current will flow and the capacitor will get charged. And if there is any load at all, it will get charged to a voltage value equal to Vin. So the minimum voltage that this circuit can produce is equal to the source voltage Vin. So the output voltage can only be higher than that, cannot be less than that. If the output voltage is less than that, the diode will conduct and the capacitor will get charged again. Now we will understand the basic operation of the step-up converter under continuous conduction mode. We will use three waveforms to understand the operation: the switch voltage waveform, the inductor voltage waveform, and the inductor current waveform. T on is the on interval of the switch and T off is the off interval of the switch. T on plus T off is equal to Ts, the switching period, and T on by Ts is the duty cycle. Duty cycle is what we use as the control parameter to control the converter. T off by Ts is 1 minus D, and you can note that the duty cycle range is between 0 and 1. We will plot three waveforms: the switch voltage Vs, the inductor voltage VL, and the inductor current IL. We are assuming that the circuit has been operating for some time and now it is operating under steady state. Let the switch be turned on. Because we are dealing with an ideal switch, the switch voltage will be 0. We are taking this potential as the common potential in the circuit. So the diode anode will be connected to 0 volts, while the diode cathode is connected to V0, and V0 is positive and higher than Vin. So the diode will be reverse biased and it will stop conducting. So a current flows through the inductor as shown, and the load voltage is sustained by the output capacitor. The capacitor is so large that as the capacitor discharges, the voltage does not dip much. So you can see that the circuit is split into two parts. One part is charging the inductor, the other part is output capacitor taking care of the load. The switch voltage is now 0 as shown. With the switch conducting, a voltage of Vin is applied across the inductor as shown. As the voltage is applied across the inductor current will change from a starting value of I1 to a new value of I2. The inductor relationship is given by VL equals LdIL by dt. So the inductor current slope dIL by dt will be VL by L. Now we are in the turn on interval, that is the T on interval when the switch is turned on. T on interval period is dTs. So the current slope during this interval will be Vin by L. Now the switch is turned off. As the switch is turned off, you are trying to interrupt the inductor current. The inductor current will fall, the inductor flux will fall. So dIL by dt will be negative, d phi by dt will be negative. A negative voltage will be induced in the inductor with this side positive and this side negative. This voltage in the opposite polarity in the inductor will add on to the Vin. that will overcome the higher output voltage and forward bias the diode. That's where the boosting occurs. During the interval T off, the input supply is connected to the load side via the inductor. The source and the inductor supply energy to the capacitor and the load. Since the diode is conducting, when the switch is off, the switch voltage will be V0. So this side of the inductor is connected to Vin. Because the diode is forward biased, this side of the inductor is connected to V0. So the inductor voltage will be Vin minus V0. So during this interval, because you are applying a negative voltage to the inductor, the current will fall, and at the end of the interval, the current returns to I1 because we are under steady state. So we are in T off interval, and the T off interval duration is 1 minus dTs, and the dIL by dt during this interval will be the inductor voltage Vin minus V0 by L. So this slope is Vin minus V0 by L. So to go through that again, when the switch is on, the circuit splits into two parts. The diode is reverse biased. The voltage of Vin is applied to the inductor, and the current builds up at the rate of Vin by L from I1 to I2. And when the switch is off, the inductor current falls. The induced voltage is in the opposite polarity. That together with the Vin forward biases the diode D, and the current now flows through the diode to the output side. So during this interval, the switch voltage will be V0. The inductor voltage will be Vin minus V0, and the slope of the inductor current will be Vin minus V0 by L. This explains one cycle of operation of the boost converter. Notice that here Vin is a positive voltage, and Vin minus V0 has to be a negative voltage in order to have volt-second balance. That means V0 has to be necessarily more than Vin for the circuit to work. In the case of boost converter, notice that the inductor is connected to the input source. The average of the inductor current, IL average, that is the DC input current, IN. This part of the inductor current flows through the switch when the switch is on. This part of the inductor current flows through the diode when the switch is off and the diode is on. So I am reproducing the diode current separately here. When the diode is on, the diode current starts at a value of I2 and then goes down to I1. Rest of the interval, the diode is not conducting, so the diode current is 0. The diode current has a DC part and a ripple part or a AC part. The AC part flows through the capacitor because our capacitor is very large. It is meant to filter the AC part. The DC part of the diode current flows through the load. So the average diode current is the load current. So I0, the DC load current, is ID average. This is the boost converter. Take a buck converter and see how it differs from a buck converter, just topology wise, just circuit wise. You see virtually the same components are used in a different arrangement. There are some very interesting topological relationships between these converters. Now, in the case of the buck converter, the inductor is on the output side, so the average inductor current flows through the load. Here, in the case of boost converter, the inductor is on the input side, the average inductor current is the source current. In a buck converter, the energy transfer from the source to the load occurs when the switch is on. When the switch is on, the input voltage is connected to the load via the inductor. The difference between the input voltage and the output voltage is absorbed by the inductor. So the inductor bucks the input voltage. In the case of the boost converter, the input voltage is directly connected to the output load via the inductor during the T-off interval. Here the inductor voltage adds to the source voltage during the interval T-off when the energy is transferred from the source to the load. The inductor here boosts the input voltage. Next, we will derive the equation for the voltage ratio or the voltage gain. We will take the inductor voltage waveform and apply volt-second balance. That is integral 0 to Ts VL dt equals 0. This is just another way of stating that the circuit is under steady state and the inductor current has to return to the initial value at the end of the cycle. This means that the area A plus is equal to the magnitude of area A minus. A plus A minus is 0. And A plus is V in times T on and A minus is V in minus V naught times T off. T on is dTs, T off is 1 minus dTs. So we can rewrite this equation as V in times dTs plus V in minus V naught times 1 minus d times Ts equals 0. We can collect the terms and rewrite this as V in times Ts minus V naught times 1 minus dTs equals 0. So V naught by V in will be 1 by 1 minus d. So this gives the equation for the voltage gain or the voltage ratio of the boost converter. The duty cycle range will be between 0 and 1. When d is 0, V naught by V in equals 1. As d increases, V naught by V in will increase. There are a few more ways of getting the same result. One other way of getting this equation is to look at the input side of the boost converter. The average inductor voltage or the DC voltage across the inductor has to be 0. That's another way of talking about the volt-second balance. So the switch average voltage will be equal to the input DC voltage. So if you take the switch voltage and then average it and equate it to V in, we will derive the same equation V naught by V in equals 1 by 1 minus t. You may want to try it out and convince yourself that that is one more way of deriving this equation. This is an idealized DC-DC converter. There is no part inside the circuit where power loss occurs. So the input power equals output power, true of all ideal converters in fact. Since input power equals output power, V in I in, the input DC power, equals V naught I naught, output DC power. So we can write V naught by V in will be I in by I naught, and we know that V naught by V in is 1 by 1 minus T. So like all DC-DC converters, this is like a DC transformer with adjustable ratio. Now let's look at the plot of the gain versus duty cycle. V naught by V in is 1 by 1 minus D. So we are plotting V naught by V in versus duty cycle. At D equal to 0, the gain is going to be 1. And as D goes towards 1, the voltage increases. The gain V naught by V in increases without limit ideally. What happens when we make duty cycle equal to 1? Let's pause for a moment and think. When duty cycle equals 1, it looks like the voltage will keep increasing and go to infinity, whatever that means. That implies that it will go to a very high value. But if duty cycle equals 1, the switch is always on. Diode never conducts. So power never goes to the output side. If there is no power going to the output side, there is no voltage buildup on the output. So the output voltage will in fact be 0. In addition, if the switch is always on, the inductor is always connected across the input supply. So the current will tend to go to a high value. The switch will get damaged. The inductor insulation may burn. So this circuit cannot be operated at duty cycle equal to 1. In fact, for practical reasons, the circuit cannot be operated even close to duty cycle equal to 1. Typically, a practical boost converter will have the characteristics as shown. This is because of losses in the circuit. Beyond the duty cycle, you will find that the gain starts to fall. So the maximum gain is limited by the converter losses. We cannot take a 5-volt power supply and boost it to 50 kilovolts. Corresponding to this, there is a maximum duty cycle, D max. If you go beyond this, as D increases, the voltage will fall rather than go up. So your control system will be very confused. At high Ds, when you go towards D max, you will find that losses in the converter will be higher and the efficiency of the boost converter will become poorer. Typically, in a boost converter, you have to place a limit on the maximum duty cycle, and the maximum gain that you can get is limited. Lastly, in this video, we are going to derive a simple equation for the ripple in the inductor current. Inductor current ripple is an important parameter in the design of the converter. I'm reproducing the VL and IL waveforms which we saw earlier. When the switch is on, the inductor voltage is V in, and when the switch is off, the inductor current goes through the diode and flows to the output side, and the inductor voltage will be V in minus V naught. During the T on interval, when the voltage across the inductor is V in, the inductor current starts from I1 and goes to I2 at a slope of V in by L. And then when the switch is switched off, the inductor current flows through the diode and the voltage across the inductor is V in minus V naught. Remember, V in minus V naught is a negative quantity. And the inductor current falls at a rate of V in minus V naught by L. We are interested in finding I2 minus I1, that is delta IL peak to peak inductor current ripple. It's very simple. Take the current slope, either the upward going slope or the downward going slope. Let us take the upward going slope, V in by L, multiply it by the T on interval, the duration for which it is going up, that will give you delta IL. Delta IL is I2 minus I1, that equals V in by L times T on. And T on is dTs. So delta IL is V in Ts by L d. Simple derivation for the ripple current in the input inductor in boost. You can rewrite this in terms of the output voltage. So V naught by V in is 1 by 1 minus d. So V in is V naught times 1 minus d. So delta IL is V naught Ts by L d times 1 minus d. This is another form for the same equation. In later videos, we will see some problems on boost converter, then the use of this equation will become clearer. With that, we have come to the end of this video. In this video, we saw the basic operation of a boost DC-DC converter under continuous conduction mode. If you like this video and the series of videos, please click the like button and subscribe to this channel. Thank you.